Okay, let's start with questions. So this is the first one called noise margins. It's a little bit complicated, but I will try to use figures, try to explain what we are asking here. Just to give you intuition, if you look at, we're talking about digital systems, like Mani said yesterday. So which means everything, the input and output should be discrete or in digital forms. So the easiest way to implement digital things in circuits is, of course, binary. You can, for example, a switch maybe consist of MOSFET. It can have two states, on and off. So which means everything is 0 and 1. That is binary. That's most common things we're talking about in digital systems. In that case, for example, I'm talking about, let's say in a CMOS circuit, we have 0 volts, which is standing for 0 bits, and 3.3 volts, which we decide is 1 bit, 0, 1, 0, 1, 0, 1. This is a square wave, simple and easy, it's plain enough, right? And another, however, in real life, the real world doesn't work in this way. Like in this problem, what we are talking about is, let's say we put two wires together. Because of the electromagnetic field, they will interact with each other. And this coupling will cause noise. Actually, the longer wire will cause some interference on the shorter wire. And in that case, it will cause some problems. So instead of this, this is ideal, right? Oh, let me use another color, actually. This is ideal case, but this is real world case where you have a very noisy signal, but our system should still be able to understand what is happening here, right? So that's why we are setting thresholds. I will take input. Let's say we are dealing with an input wire. So I'm having threshold, which is input lower threshold and input higher threshold, which is VIL and VIH. So let's put it here. So I set a threshold here, which means every signal below this threshold is decided as 0. Similarly, everything below beyond this threshold is deciphered as 1. So let's give you an example. So once I have set these two thresholds, you can treat the the black curve is an input signal, but this is how with these two thresholds, this is how electronic system will, or digital system will understand it. So everything below the threshold is going to be 0, and until we reach here, where we determine everything as after that as 1, and until here, where we have the threshold is no longer 1, it's going to be 0. And again here, so it goes up again. I'm not going forward, but you can see actually a noisy signal becomes a perfect digital signal again. That's why we are having this threshold. It's because we inevitably have noise, either from thermal noise or from interference from other wires, but we can try to use this kind of thresholds to make it more clear. Okay, so let's move back to this problem. So we have a few things. So as we increase the voltage, so we are increase the input voltage over here. So if ideally we have 0 volts, which is V0, and also V1 in our example is 2.5 volts. That is a standard value of the ideal case. Zeros and ones should be like this. And we have V minimum. Let's say we have, this is our normal signal, but then we got some interference, which is makes the signal look like this. Then you can see once it passed the minimum threshold, it will cause damage. That's clear, right? So in order to avoid this, the first question is asking you the following, which is, if the victim is at VOL, or VOL is at actually here, this is the victim signal. So I would say the first question is very easy, just how to say, bon appetit problem. And the aggressor means the interferer, which something tried to sabotage our system. It can be a strong interference or longer wire, and it want to push it down. And how far can we go? We can go down to here, right? We can go down here. Can we go further? No, right? Because we will suffer from some damage. So there was some damage here. Okay, so how much can we push it down in the end? Any ideas?
0.5 volts.
Yes, that's very nice because we have 0.2 volts here. What is V minimum? Because it's minus 0.3. So this difference is 0.5. Thank you. May I ask who's speaking?
Kratik.
Pratik. Thank you, Pratik. Got it. Anyone with any questions with the first question? Oh, that's so no more questions, right? We can move forward. And let's look at maybe problem B. Oops, sorry. Okay, so if the victim Y is at 0 volts, actually I would say the rest of the problems is very similar. Oh, by the way, I just want to explain my annotation here a bit. So you can see if a system, a signal is beyond this threshold, is deciphered as 1, or is below this threshold is 0. In between is non-decided, which is some noisy states we can try to ignore. Okay, so we start at 0 volts and we want to push it down without causing a problem. So how much we can go this time? This is 0, this is 0.3. Any volunteers?
0.3.
Thank you, Jake. Yes, 0.3. So again, this is 0.5. This is 0.3. Okay, the third one. Nice. So if the victim Y is at VOH, I'm just basically draw it here. The table I converted into this figure. So the victim is currently at VOH here, and we want to push it down without causing a problem. So any thoughts how far we can go in that case? I think these questions are all similar.
I don't know what the difference between OH and IH is here,
Oh,
but it might be, yeah,
yes.
it might be a 0.4 or 0 or all the way down to the damage. I'm not sure what counts.
That's a very good point. Actually, I'm missing 2 lines here because sometimes for input we have a lower threshold, which is let's draw it here. VOL is 0.2 volts. So this is 0.2. And we have another one which is should be VIL, that's 0.7. So I can draw it here. That's VIL 0.7. Another one is VIH, right? Oh, sorry, it's too crowded. I'm afraid. Let's move it up. Okay, this is VOH. Finally, we have something here in the middle that is should be VIL, which is VIH, which is 1.7 volts. Let me draw it here. Okay, VIH 1.7. And finally, this is VOH, that is 2.1. Okay, so we are now at this position. And okay, by the way, this is still considered to be 1 and this is considered to be 0. Only in the middle is undecided. So what do you mean by causing a problem? Causing a problem, which means a 1 is no longer 1. It becomes something cannot be deciphered, or it becomes 0, right? So we can go down only to this threshold, if you agree with me. And this gap is, if I'm correct, is 0.4, 2.1 minus 1.7. Any question here?
What is the difference between the input and output thresholds, though, or what do they represent?
Okay, so if you look at this figure, this is for input, which I think I explained the the intuition before, and because for input and output, because let's say any logical gates, for example, an AND gate, we have some inputs, we have outputs. So for inputs and outputs, you might have different standards because of the circuit design. And for the input, sometimes we can relax it a little bit because we want to accommodate more. But for our output, we want to be more perfect. So which means we have 2 more thresholds here. That is the OH. Sorry, This is a lower threshold, VOL and VOH. So we might have a tighter threshold. This is for output.
Okay, so if you had some sort of logical gate, you're saying that the input would need to be within those thresholds, but then the output would be somewhere in between the output thresholds.
Yeah.
Okay.
So yeah, for output, the requirements is actually higher. But here we are talking about some minimum, which is the minimum things. Let's say, because one gate can be connected to another gate, right? So which means as long as let's say that's my output voltage. And because my some interferences might go down to here, which is I'm drawing, and it actually doesn't satisfy my personal standard for output. But for the next gate who is taking my input, that's still sufficient. Does it make sense? That's the case where we have voltage follows here. It won't. That's why I say it won't cause a problem, but it's not, of course, not what we want. That makes sense? Okay. If I have a permission, I should move on. So the last one is the V-term Y is at VDD. VDD is defined as V1, which is 2.5. This is VDD. And aggressor want to push it up. And how far can we go here before going to damage? What is Vmax?
Yeah, sorry, on the last thing, on A even here, if we account for that being the input, then would that be 1 volt as the delta that you could get before you damage it? Oh no, we said it's a VOL. Never mind. Yeah. Okay. Never mind. You defined it there. Yep. Okay.
But here we are at 2.5, and the next the threshold is 2.8. So how much do we have here? 0.3, right?
Yeah.
So again, this is just simple. The key problem, the reason I'm putting this question is for you to understand the difference from ideal circuit you design and actually it will behave in the real world. That's why we have this noise threshold, trying to understand, let you understand, sometimes we suffer from some interference, and how we need to design, take this the budget into our design considerations. That's a key concept. But generally, how you solve this kind of problem, just you found where you are and you see where are the threshold that won't cause a problem. Let's say this is where I am, and I want to output a 0. So if I go down, I can go down at most to here to avoid damage. If I go up, I can go at most to here to be able to, say the next gate can take it as 0. So that's the boundary which it won't cause any problem. And I'm basically asking about how far can we go up, how far can we go down. I might miss. Yeah.
Sorry. Is the reason why we can't go past the middle point is because if you did go up a certain amount, then you'd be in that undefined area?
Yes, it will cause confusion for the downstream circuits. And in worst case, if you even exceed this threshold, it will actually give you a wrong number. Let's say we have 0, 1, 1, which is 3. But if I give you 1, 1, 1, it becomes this is 7. You see the difference, right? So which means just one bit is incorrect can cause a lot of problems downstreams. So that's why we will try to avoid this. That makes sense?
Did you say if the wire's at VOH, it would be 0.4 is the amount you could push it down though, or?
See that?
Or was that from some other problem?
Oh, I mean here?
Yeah.
Yes, in this example, it is because we are already here. So there's not much space we can go down.
Oh, you can push it down to the input threshold. I see. Okay.
Yeah. But again, this is just example. The real world numbers might not look like this. Just want to make sure. It's just example question. Okay, let's move on. But before I move on, I would give you a hint. That is, all the rest of the problems can be solved in this way. That's what we I personally take as some digital mind, which is everything is in binary bits. So imagine we have 1 bits. How many numbers can we represent? There's only 0 and 1, right? Which is 2 numbers. So what do we have 2 bits? We can have 0, 0, 0, 1, 1, 0, 1, 1, which on each position, we have 2 possibilities. So it's 2 to the 2 equals to 4 possibilities. And what about 3 bits? We can add a 0 here. What I can do is just copy the lower 2 bits, right? Let's paste it here. And 1, 1, 1, 1. I get a 0. This is how is it, decimal 0, 1, 2, 3, 4, 5, 6, 7. So we can represent using 3 bits, we can represent each numbers from 0 to 7. That makes sense. Again, which means the number of decimal numbers we can represent using bits. It's actually 2 to the n is the bits, which is like 6 bits. You have 64 numbers you can represent. I hope that makes sense, right? Just for every bits you have, because it's binary, you have 2 choices for each position. But that there's no rule saying for digital system we should use binary. Let's say trinary, which we can have 0, 1, 2, and let's see 2 bits. What happens next is 1, 0, 1, 1, 1, 2, and we have 1, 0, 0. That makes sense, right? Still, in this case, it's going to be 3 to the n, which is trinary. It doesn't have to be binary, but because, like I said, binary is easier to implement. A switch can do that, on, off, on, off. So that's why I'm using binary. 20 would be after 12. Jake, do you mind explain this question a bit?
Oh, I just meant if we were using a trinary system, you would have 2 zeros, the next number, I think.
Sorry, my mind is binary, my bad. Yes, 1, 2, then 2 plus 1, 3. So we get 0 and 1 and 2. You're right. And 2, 1, 2, 2. Then it's 1, 0, 0, right? Okay, thank you. That's good catch. Okay, if you we don't have any more problems, we'll move on. So this is called something called a Greek code. Wow, this is again a very long description of the problem. But I will just, if you look at here, we have, I will just try to explain the question verbally. So we have these temperatures, room temperatures in Fahrenheit, I guess, and in incrementals of 2 degrees. And we try to use, like I said before, we have 8 different temperatures. So how many bits is required, minimum bits required to represent it? Remember 2 to the n greater or equals to 8, right? So n, the minimum n should be 3, if you agree with me. So 3 bits is enough. So again, we are just using binaries 0, 1, 2, 3, 4, oh, sorry. Okay. Ideally, well, this is what I can do. 0, 0, oh, that's 2, sorry. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 0. What should I put here? 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. That's normally what we'll do. This is natural, right? We just increment by 1 each time. What's the problem with the red things? Any thoughts? Well, I guess it's too hard. Sorry, I shouldn't have asked you because you need some experience to answer this question. Let me switch to next page to understand how will I create these numbers in circuits. Generally speaking, you will learn how to do these circuits easily in the future. But I'm just, give you example. This is the first, you can call it clock signal I'm using. So I'm just swapping between 0, 1, 0, 1, 0, 1, 0. That makes sense, right? So it's just a square wave with duty cycle 50%. And then for the second clock, I'm going to halve the frequency, which is 0, 1, 0, 1. And the third one will be even slower, 0, 1. And if you want to have more bits, you can have something like this. Then when we summarize it, if you look at it vertically, what we will have is this is 0, 0, 0. The second one will give you, let's go this direction, then 0, 0, 1, right? If you look at here. So the third one will be 0, 1, 0. The fourth one will be 0, 1, 1. So you can see the fifth one is going to be 1, 0, 0. So it's naturally a counter, which is increased number by 1 each time. It's called X6 for, sorry. This kind of pattern for the duration of the zeros. 8410. if I have one more bits, I can make it this way to make a counter. So the lower one will be the higher bits. So this is the highest bits. This is the lowest bits. Okay, sounds very good. But what if, let's say, this kind of logical gates, they are implemented using actually circuits, which are transistors, right? So we know this kind of things will have delay. And the more complicated your circuits are, there's a higher chance where you suffer from more delay. So let me just copy this example and probably paste it here. Okay, let's say if we have a little bit delay, so let's say our second signal is delayed this way, and our third signal is delayed here. What will happen? So you can see we have some confusion I will highlight one position, which is here. Is everyone still following me? So I'm starting from the transition from which is 011 to 100. Can anyone tell me how many bits changes simultaneously here? That's 3 bits, right? So we have 3 bits changing simultaneously, and it will cause problems because of the delays. So let's see, in the end, what we have in this region, we have actually in 4 regions. Let me move to the next page. This is the same figure, but I created it before to emphasize. So this is where we start. We start from 011. Everything looks good, right? And here we end at 100. This is which number is this in decimal? 3, right? Oh, by the way, have I told you how to do this conversion? Okay, let's say I have something 10101. Then I want to convert this one to decimal. How do I do that? Is you can just 1 times, this is 0, 1, 2, 3, 4. Okay, 1 to the times 2 to the 4 plus 0 times 2 to the 3 plus 2. Oh, sorry, my bad. 1 times 2 to the 2 and 0 times 2 to the 1. Finally, 1 times 2 to the 0. So that's the final decimal number you're going to get. So in this case, we have 1 plus 2 equals to 3. That's simple, right? And here 100, so it's a third 0, 1, 2. So what I'm going to get here is number 4, right? So that's what we want in this case. So I start from here and I want to arrive at here. This is 3 and this is 4. This is clear enough. But the problem is there are 2 states, transitional states inside. And let's look at what we have here. This is 0, this is 1, this is 0. So we have 0, 1, 0. Can anyone guess what the number is? Not to guess, calculate. I think this is what I'm getting in this interval. Sorry?
3. No, 2.
Yeah, it's a 2, right? And how about in the middle interval? I got oops. Yeah. In the middle interval, which is here, what we are having, the highest bit is 1, right? Because it's high over here. And the second bit is also high, it's 1, and the third one is low. So what's the number we are getting? 1, 1, 0. If I'm right. Can anyone verify this? So it's high, high, and low in the second interval. So in this case, what I'm getting is, what's the number?
6.
This is 4, this is 2. I'm getting 6, right? So finally, if I have something to print out my results, it's going to give me, instead of 3 to 4, it's giving me 3, 2, 6, 4. Wow, that's definitely not what we want. Imagine you are looking at a watch. It's now 3 p.m. Now it turns to 4. It becomes 3 and 2, then 6 and 4. That's going to cause problems. The root cause of such problem is because from 001 to 110, oh sorry, not 011 to 100, we have 3 bits jumping simultaneously. So that's why there are some smart guy called Gray, which they are proposing, what if I can change only 1 bit every time from one number to next number? Okay, and this question is just to ask you to design 3 bits grid code. In short, that's what we are asking for in this question. Is everyone clear with the definition of grid code, which is for adjacent numbers? By numbers, I mean decimal numbers, or the states you want to represent, which is from, let's say, 3 to 4 or 5 to 6. We want only 1 bit to change. That's called a grid code. Only 1 bit change in adjacent numbers. I'm afraid you are going to have to remember this definition in the future. And so let's give it a try. I can do it together. I want to do a simple one, which is how about 2 bits? Can anyone give me some thoughts? Let's start from 00, for example. What's going to be next? Remember, this is decimal. We only change 1 bit at a time. So we start from 0, 0, and what's the next one going to be? Any thoughts? 01. Thank you.
01.
Yeah, 01. And which one we use to represent 2? Can we use 10?
That changes 2 bits.
Yeah, that's a violation of our rules. Remember, only 1 bit can change. So it's 11. Then finally 10 for 3. This is very simple and easy for 2 bits. So any thoughts for 3 bits? Just to give you information, grid codes are not unique, which means you can have different rules to create different. The order is not unique, which means because we have 8 bits and they are used all, we use them all. So there are only 8 bits, but the order can change. But this is one way I personally found very powerful to do this, which is, let's say we have 00. Maybe what we should do first is to try it manually. Let's say we start from 00 and 001, 011, 010. This is what we just do for 2 bits. I'm just adding a 0 and for the first row. Can anyone give me an example or what's going to happen next? Like I said, there can be one more answers.
You could put a column of 1s and then just kind of count downwards the opposite way. So you do 1, 0, 1 and do it in reverse.
Great. Okay. Since someone already jumped through to the, the more systematic approach, I will directly introduce that one instead of bothering with this brute force methods. So yes, that's a good catch. Because let's ignore the first bits. Because if you agree with me, the next 4 numbers should be always have the 1 at the beginning. If that's the case, right? Because we only have 8 numbers. Now 4 zeros has been used for the first bits. The rest has to be 1s. Okay, then we cannot do 00 here because it's a violation of the rules. But like, sorry, who was that? Who was that? Just help me.
Really?
Julie, thank you. Yeah, just like Julie said, what we can do is just copy it and go in a reverse manner, which is 11, copy here, and 01, 00. Because remember, from here is going to change 1 bits only. And if we move it back, it's still 1 bits only. And there's no bits change at the beginning. And in the between, because we are copy this, then we have a transition from 0 to 1. That's suffice our rules. See, why I call this a systematic approach? That's because, what if I want to get another bit? A 4 bits grid code, can we generate in the same way? We can, right? Because it's the same, it's recursive. Now this is a grid code for 3 bits. I will add zeros for all the first one, and again, a lot of 1s. Then I just copied 100, 101. Sorry, what's the next? 111. What's the next? 110. What's next? 010. So on and so forth. So which means you can infinitely create a whatever number of bits I'm asking for the gray code. So that would be a more system approach. But again, this is not only solution. Even personally, I know there's another systematic solution for this question. But I'm just providing one way, which is easy to, how to say, remember and implement. I hope that makes sense to you. Do I have your permission to move on? Okay, thank you, everyone. This is a simple question I'm going to have. Remember the hints I have here. How many bits, how many different states can represent using binary? So, which is pretty simple. Just for, I know a few, we have many international students in the class. So here, some definition that suits and a rank. I'm only consider there are 52 cards, which is from 0 to, wait, there's no 0, 1 to 10 and plus J, K, Q. That's 13 different cards. And we have 4 different types: the blackjack, the heart, the square, and what's the fourth one? And so this is so the number is called the rank, and the 4 sets is called 4 suits. That's the definition I'm talking about here. That's clear, right? What is rank? What is suit? What I mean here. So I'm not talking about jokers. Let's temporarily remove them from the pile. Okay. So firstly, we're asking about, we want to represent the cards in binary. Binary only zeros and ones. Then how many bits do we need to represent these 52 cards? Any guesses? Remember our hints?
8 because it's 64.
Again? I didn't catch that.
8 because it's close to 64, because 52 is like, that's pretty close.
It would be
64.
6, right?
Or it'd be
Two to
6.
six.
Oh, 2 to the 6.
Yeah, but that's
Yeah, there you go.
good thoughts. Just 2 to the 6 is 64. 2 to the 8 is already 256. But yes, you can see with 6 bits, we can represent 64 different cards. But what about 5 bits? 32, right? It's not sufficient for us. So the first question is 6 bits. That's so simple, so easy, right? Nothing special here, just how many bits do we need? Okay. And then for B, we want to simplify operation. So which means we want it easier to represent the same suit or rank. So what does this mean? Which means I have 2 cards. I want to make it easier to compare. Do they come from the same suit? Do they are they from the same rank? The size are the same. So what are the initial thoughts you can have?
I think like if we wanted to do like 10 of spades, we could have 4 bits that represent the number. So it'd be like 1 through 13 technically.
Mm-hmm.
And then the next 2 bits can represent different suits. So like if we would need 2 bits there. So like a 0 would be spade, 1 would be clubs, etc.
Thank you. I think you directly give us the right answer. So let me repeat. So if we want to do this comparison, of course, we want to separate the information. So we don't have to compare 6 bits all the time. We can split it. Then for we need 4 bits. Why do we need 4 bits for? Can anyone else tell me why do we need 4 bits for numbers? How many numbers do we have?
The rank can go up to 10. Well, and then we also have the other. So we have 13 ranks.
Yeah, the number is 13. So 2 to the 4 is 16, greater than 13. So we have 4 bits for numbers. Then we only have 4 suits. So which is 4 suits. Then we need 2 bits. I think that part is easier, right? We have 4 suits, so 2 bits to represent it. Then in total we still 6 bits, but now it's 2 plus 4, 2 for the rank, 2 for the suit, 4 for the rank. Okay, finally, there's a small question. Actually, it's some extension saying, if you want to check 2 cards are adjacent, are we going to, how about we revisit this in the future? But currently, anyone has any thoughts? So how do we know that if we are looking at 2 adjacent cards?
If we're using the second representation, we could just look at the two numbers or the second 4 bits.
The second
Um,
is, yeah,
And
Let's-
then,
3 and 4, we have 0.
yeah, just check if they're next to each other.
Uh,
Or two numbers that would be next to each other.
yes, but in this case, you might need to compare, 4 bits. That would be one solution. I do agree. That suffice for answering this question. But there are also other possibilities. We will, like I said, I will come back to revisit this problem in the future, maybe let's say next week. But one way, but thank you for this answer. This is correct. For if if this is exam, I will give you full credits for this. But another thing you can think of to make things slightly easier, maybe the first, remember we talked about the gray code here? Remember, gray code is as efficient as sequential code or binary codes, right? Because we still use 3 bits to represent 8 numbers. It's just we only change 1 bit every time. So if we know that there's only 1 bit difference between these 2 numbers, then we know it's the same. Or I want to dive into these. So how do I do this in circuits? So one way I can think of immediately to do this is, remember I have 2 cards. So I can just, let's say A and B. I can use some circuits to calculate A plus 1 and B plus 1. Then I just compare these 2 pairs. If they are a match, then I will get, we know the difference is 1. If you agree with me. This is just about how to implement this, but in the future, you will learn how to design combinational circuits to solve this kind of easy problems, but that's just some hints for the future. Okay, so we are a little bit short of time, so can I move forward? This is a very simple problem, right? Just remember 2 to the something, and you need more than that to represent all the different states. That's all I want to take away from this question. Next one, something very interesting, red and poison. So 1000, can anyone read this for me? Any volunteers?
Yeah, I can.
Thank you.
There are 1,000 wine bottles. One of the bottles contains poisoned wine. A rat dies after 1 hour of drinking the poisoned wine. How many minimum rats are required to figure out which bottle contains poison in 1 hour?
Thank you. Can anyone give me a brute force answer firstly? I know there's
1,000.
of course 999, right? Save 1 life. Okay, but yeah, can we do better than that?
Does it depend on how fast a rat can drink?
Well,
Yeah.
let's set another threshold. I allow you to mix the bottles, but 1 rat can only drink once per hour. But otherwise, this is what I heard this morning, which is very clever. But let's say we said we have around 100 rats, right? So I have a timer. Then I ask 1 rat to drink one bottle every, let's say, 5 seconds. And I will calculate when it dies. Then I know which bottle it drank to cause the death. But that's cheating. But you theoretically you just need 1 rat to do that. Okay, I don't allow you a timer, and I only allow 1 rat to drink 1 sip every hour to avoid this confusion. Okay, any thoughts?
You could start by mixing half the bottles with each other.
Half the bottle with each other, yeah. But we can only test once. Remember, the rats only die. It's 1 hour, and it takes 1 hour to take the effect. I do agree. This kind of binary search.
Yeah, could you mix half the bottles and have half of, or I guess you would have 500 rats. Try 1 of those each, and then 500 rats. Well, it'd still take the same number of rats. Then.
But you're getting a little bit more. And mixing, what we can do is encoding, right? So which means we can have 1 rat. Let's say we only have 2 bottles, and 2 rats. So what I can 2 bottles with A and B, let's say. So, well, there's 3 bottles at least, A, B, and C. So I can ask the first rat maybe drink these 2, and the second rat to drink maybe B and C. Let's see what will happen. So if A is alive, or sorry, R1 is alive, what does it mean? Oh, how many states can there be actually? You can see this is something binary, right? The rat can after 1 hour can be live or dead. So let's give you example. If I have a rat R1 to drink the first 2 bottles and R2 to drink the second 2 bottles. So what will happen if we have 0, 0? And that's not possible, right? Because which means none of them is poisonous. What about 1, 0? Well, 1 means
A has to be poisonous.
let's see, one means death, okay. So R1 died and R2 is alive. Is that possible?
Only if A is the poison bottle, right?
Okay, yeah. So then we know A is a poison bottle. What about 0, 1? What do we have? I think that indicates C is the bottle. Or 1, 1. Is that even possible? Oh yes, that's possible because everyone you have to drink B too for this, right? You can see we are doing this kind of encoding for the bottles. So which means I'm using A, B, C. Does it ring a bell? Now we have like 1,000 wine bottles. How many minimum rats? You just need to encode to create these states. You need to
Log base 2 of 1,000.
you need to create how many states? 1,000 different states of life and death, non-overlapping, right? And each rat can be either alive or dead. And how many do we need? Oh, maybe just, yeah, maybe it's just this calculation bother you. 2 to the 10 is 1024. Yeah. So n equals to 10. But I know that example still puzzles many people. So I will give a more systematic example, which is I have, let's say how can I use 3 rats to detect 8 bottles? I will give you an example like this. Okay, so I have 8 bottles. I call it B1, B2, B3, B4, 5, 6, 7, 8. Wow. And we have rats R1, R2, R3. Okay, or we just encoded, right? Of course, if you like, you can use gray code, maybe save more lives. Sorry. What's next? 0, 1, 0, 0, well, sorry, 1, 1, 0. Do I made a mistake here?
I think B5 would be 1, 1, 0, right?
You had
I must have missed 1 number.
0, 1, 1.
Ah,
4.
no. Okay, thank you. Okay, how about I drag this part a little bit down? Okay. Oh, sorry, 0, 1, 1. Okay, great. Then what does the encoding means actually? Okay, so for rat 3, what's it going to drink? The following. Remember, 1 means dead, 0 means alive. So for R3, I will ask him to drink a combination of B2, B4, B6, and B8. Similarly, for rat 1, it's going to drink 5, 6, 7, 8. That makes sense, right? And let's take example. After all the tests, we got this thing, which means R1 is alive, R2 is dead, R3 is dead. Then that means which one is poisonous? So R1 didn't drink before and it's alive. R2 and R3 both drink before and they are dead. So before is poisonous. That makes sense, right? Similarly, if they are all alive, that means B1 is poisonous because no one drank the B1 and no one died. We know there's 1 poison. So
well, is it that they drank it or that they're alive or dead? Because if they didn't drink it, then how would you know if they'd be alive or dead?
Okay, here for vertically, each rat will drink a combination of many bottles. And after 1 hour, we are looking at the consequences. We are looking at the results.
Are they all drinking every bottle?
No, they are following this pattern. So if we have a table here. So vertically means which rat drink which bottle. And horizontally, it also means live alive or not. That makes sense.
How would you know if B1's poison or not if no one drank it?
Because there's only one such bottle, which is not drank by anyone. That's 0 and 0, 0, 0, which is B1 is not drank by any of the rats. And if all the rats are, hold on. Okay, that's a good question.
Yeah, if all of the rats are alive in the end, then that means B1 had to be the poison one because nobody drank it.
I understand, like well, if there was no, like, because B8 they're all one, so they all drank it and died. But
I see.
No,
B1 was never drank by
we're
any
saying
rat.
if B1 is the poison bottle, then that means all of the rats
That's
will be
right.
dead.
The thing is, we have only one of the bottles is poisoned. So which means, let's say we only the first bottle is not drank. And whatever the rest, if you drink them all, that's fine, right? No one's going to die because of that. So by exclusion, we know that there's only one bottle, and that is poisoned. If that makes sense?
Yeah.
Because that only works because only one of the bottle is poisoned. If there are multiple bottle of poison, of course we cannot do this.
Okay, but then how? Because one is a dead, yeah. That means some bottles that aren't poisoned, they're drinking and dying. No,
Not really.
Because each rat drinks two
for
bottles,
B7,
right?
for B7, we have rat 1 and rat 2 are both dead.
No. Okay, that's horizontally. This is so. We firstly let the rack drink in the vertical order, which is like
Yeah.
R2 to drink this combination, and we observe the results. Only one of these 8 cases can happen. If you agree with me, because we are doing such encodings, only one of these cases will happen.
What do you mean? Only one of the cases will happen?
We have 3 rats, and they can be only
Yes.
dead. So they finally, after 1 hour, they will give me a result that is 0, 1, for example, 101. Then I know this scenario happens. Then I know B6 is poisoned. If they are all alive, then this 0, 0, 0. That means this case happened. Then B1 is the case.
Oh, so wait, where did we determine what the case that it's poison is?
Well, we're trying to figure that out. We're like given states of their
Let's
aliveness at the end.
We are
Okay.
We encode this using
Okay. I understand.
The lives of the rats.
I understand. Okay.
So their final consequence is going to show us one combination that is telling us which code is matched.
Yeah.
This is just thank you, Logan. This is just the table to check your results against.
Right,
So we're not using it's not like how we were doing it before. Really?
Yeah.
Okay.
Right. Original question though, how does this scale up to 4 hours? Because if you were to do, assuming each rat could drink once per hour, if you did it with 2 to the 10, or if you did it with what was it, 10 rats, each would have to take 10 drinks, which would take 10 hours. Right here it works.
Oh.
Yeah, but the mixed bottles here work because each rat does 4 drinks. But if you scale it up to 10, each of the 10 rats still needs to do 10 drinks to get 2 to the 10 table, to get the table size of 2 to the 10.
Yes, I'm afraid yes. But you can think of this way by mixing it's lethal. So if you take a little sip, it will die. So I know it's not very humanitarian to ask him to drink 100 bottles, but just we're just doing some hypothesis to just for binary coding this major Q.
So we're just saying that with the time constraint of 4 hours, it's not possible then to do it in 4 hours with 10 rats because each rat needs to do 10 drinks or 5 drinks.
No.
Right, because in this case of 8 bottles, each rat needs to do 4 drinks. So you can do 8 bottles in 4 hours because each rat Right, R1 still needs to take 4 sips of fluid.
Oh, you
to
can,
test this.
but you can mix it and let it drink it all. Right?
Right, so you drink its whole batch. Okay, that makes sense.
Unfortunately, you have to do.
Yeah, that makes a lot more sense. Okay, great.
I'm sure this kind of experiment won't pass any IRB approval for ethylene to just. Okay, just. That's just.
Yeah, no, that makes sense though. I missed the
Okay.
mixing step. Great, thank you.
Okay, maybe we can move on. Again, this is how we encode. Again, we create this table, encode the bottle using the lives of the rats. And then we ask the rats to drink accordingly. And then finally we will get results and we will just compare results against this table to know which code is being matched. And we know which bottle is poisoning. Okay, another one. Everything remains same. 4 hours. What do you think will change? Remember in the previous one, we have log 2. Oh, sorry. 2 to the n is greater than 1000. What about 4 hours? So which means you can now drink 4 mixtures for each rat. But again, no, I don't give you any timer. So don't use one rat to do them all.
Could we just divide the number of well, oh, never mind.
You mean this one? Do I do it by 4?
No, I was thinking divide the number of the number of wine bottles by 4, yeah. But then you lose rats in each experiment, right?
Yeah, this will.
Oh, if you lose a rat, then you figure it out, though, right?
We always consider the worst case, which is maybe the last, only the last combination in the 4th hour worked. So, which means, yes, this is one solution. This should give you 6 bottles if I'm correct. This is 250. So 2 to the 6 is 256. So we need 6. But I can propose you something slightly better, only slightly better. Remember, when I talk, when I give hints, I talk about there's not only binary, but also trinary, or maybe quinary. In this case, is it possible? Let me explain what I'm saying. So we have 4 hours, right? So for each rat, I can define the following states. If you're following me, 0, 1, 2, 3, 4. This means 0 means alive. 1 means drink at beginning, which drink at zeros, and die. Oops, sorry. Because we can only do 1 experiment per hour. So die at the first hour. And similarly, it means drink at the first hour and die at 2nd hour, and drink at the 2nd hour and die at the 4th hour. And 4 is so unfortunate. It's why the first three experiments. In the last one, unfortunately, it died. It makes sense, right? Each rat can do 5 experiments. Okay, so in this case, how about we do the same, but then we can encode it using quinary, which is 5 incrementals, that is 0, 0, 1. I was still using 8 ball, maybe. Actually, I think 2 rats can do a lot of bottles in this case. Let me explain it. So let's try to do encoding. How many coding can we have? 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. No 5. Sorry, I missed. There should be a 0, 0, and 4 means 0 and 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, and 2, 0. How many combinations can we here have for 2? Which is 5 to the 2 is 25, right? So which means we can encode 25 bottles with only 2 rats. So how can we do it? This is B1, B2, B3, B infinite, and R1 and R2. So again, this means we follow this order to drink. We ask rat 2 to drink B2 at the beginning, and it should also drink this is B5 on the beginning of the 3rd hour, so on and so forth. So again, because it's no longer binary, but there are 5 possible states for its rats. And we can encode all of this using these 5 states. So which means we are still using numbers to represent all the bottles, but now it's no longer binary, it's quinary. So any thoughts? How many bottles? Or just give me the equation. It's quinary, right? And so any thoughts? How many rats do we have? Do we need? It's still 5 to the n, right? This is a max number of bottles can we represent using the life of the rats. If you agree with me. Again, each rat can represent have 5 different states. And if you do the encoding carefully, we can have 5 to the n different states. Should be greater than 1000. Then, well, actually 5 to the 4th is 625. So I need n equals to 5 because I need to cover all the states. Does it make sense? I know it's slightly more difficult. Before, the only difference is here. The encoding, everything's the same. Just before, we only have 2 states. After 1 hour, a rat can be either alive or be dead. But now it can be, you know, all the way alive, die here, die here, die here, die here. We have 4 hours, 4 trials. So that means we can have 5 states per rat. Then we are using quinary to encode the whole bottles. So it's 5 to the n is greater than 1000. Of course, n equals to 5. That makes sense? Can I go on? Okay, if no more questions.
That would be done. The answer for that would be 2 rats. All we need is 2 rats.
Which one?
For this, with the 5 to the n using the, we'd only need 2 rats, right?
That's if we had 10 bottles, I think.
You mixing them, yeah.
It's 1000
right?
bottles. So this
1000, yeah.
This is a minimum number because 5 to the 2 is only 25. You can only cover 25 bottles. We have 1000 to cover. You need more rats. So I think you need at least 5 rats.
Okay.
Make 5 to the 5. This is you know, a few above 3000 bottles you can detect.
Okay. So 5 rats.
Any more questions? Oh, by the way, thank you, Nikolai, for the comment. I didn't see it before. Okay. The next question. Oh, before I move on, there are something I have to preview you a little bit for. Many might cover this tomorrow, but well, it's very simple, so I would rather, you know, directly tell you about this. So guys, I need your attention here. It's going to be these things are going to follow you all the quarter. So if you don't get this right, it can be catastrophic, but it's very easy. Just say we have so many gates I have talked about, logical gates, which means we have some input, maybe 1, maybe 2, maybe more, and we have some output. That's what logical gates does. And for logical, we have NOR gate, AND gate, OR gate, XOR gate. Let me explain it one by one, but these are the symbols I want you to remember. But I can teach you a trick, very easy to remember them. So let's only look at the first one, AND gate. AND means A and V, that is, you can see this thing is called truth table. You're going to use it a lot in the future. Truth table, very important. Basically, just give you all the possible inputs. What are the potential outputs? It's a table of this called truth table. And you can see by here, what it's doing is just the A. Oh, I use this one to represent, please don't, I know it's for binary, it's just a multiplication, but don't take it as a multiplication. It's just AND. I know because I see someone ask, can I treat it as multiplication for binary? Yes, but I prefer not to do that. What if it's trinary? It will cause problems. But this is AND, and AND means you can see unless all the inputs are 1, otherwise we will output 0. That's simple, right? So which means what 0, 1, 1, 0, 0, 0 will always give you 0. Only 1, 1. Oh, sorry. Only 1, 1 will give you a 1. So 1, 1 gives you 1. Otherwise 0. Is that simple? So it's like a D shape. Look like this. It's an AND gate. What we're dealing with. The second one is called OR gate. Compare the difference. You can see it's, you know, have a curve, on the left hand side. Oh, sorry, my bad. My hand drawing is very bad on the iPad. But this is the OR gate we're talking about, which A or B. This is OR. Remember, we have a C dot here, central dot here, but we have a plus, which is for binary. You can of course think is OR because 0 is only this will give you 0. Otherwise, if any of the inputs is 1, I will have output 1. Whatever the next the other input is. So it's OR, which means as long as there's one positive in input, the output is going to be positive. So I think we are good with we're good, right? With and OR. So this is XOR, which is a little bit interesting. It's used to compare whether two inputs are the same or not. So if you can see here, if different, it means it's going to be 1. If the same, it's going to be 0. So compare if the two inputs are same. That's a okay. Then that's a trick I'm talking about. Whenever you see a small circle at the output, it will invert it. So remember, this is called an NAND get, not and. But it's called an NAND. I'm just help you memorize it. NAND means not and. So I'm adding a not here, which means it's remember what's happening for the OR gate. 0, 0 will give 0, 0, 0, 0, 1. This is for AND gate. So NAND means the opposite. So I just flip the output. That makes sense? Similarly, this is just the NOR gate. Remember, this is where the circle comes from. NOR gate means flip it, invert it. That's very simple, right? And finally is NOR gate, NOR, which is, remember, this is this is OR gate. OR gate, remember, if there's any 1 in the input, we will output a 1. This is OR gate, and NOR means I'm just to flip it. So zeros become 1 and 1 becomes zeros. Simple. There are that's only the 6 gates I want you to understand here. Remember, just to remember to check if there's a circle in the output or not. If there is, means we flip the output. Just a little bit trick. Let's go back here. Summarize. NOR gate, just flip it. That's simple, right? And AND means it's only one output 1 if the both inputs are 1s. Or this more how to say, more welcome, which is if there's a 1, then I will output 1. XOR means I compare whether they are the same or not. If they are the same, I will output 0. If they are different, I will output 1. And finally, NAND is just you can treat NAND in this way. It's just the AND plus the NOT. This is NAND, right? Nothing special. Similarly, NOR is all plus NOT. By the way, this one and this one, I would say you can use just, let's say, NAND. It can be used to consist any of the rest gates. Same for the NOR. So if I only give you the NOR gates, you can reproduce any logical circuits human have ever made. If you have any of either you have NAND or you have NOR. Make sense? You might have this as a homework in the future, but I'm not sure. I haven't seen the homework yet. But that's what I do when I learn this course. Some mind trying to train your mind, but I don't think exams will cover this because we focus more on systematic approach rather than test you are clever or not. That's not what we need to do. Okay, so if we are good with this truth table, I can give you an example here. I don't want to give answers. Okay, you don't see anything. Okay, you don't see anything. Okay, so what's this gate? Can anyone tell me?
NAND.
Great, and NAND. What's this?
XOR, whatever it is, however you say it.
XOR. Good.
Yeah.
This one? Watch out for here.
Nor.
Nor. And this is,
Not.
oh, I forgot to say not. This is how I represent not. Put a bar on top of it. Remember, the bar should cover whatever you're including. Let's say A, B. This is A and B, right? A and B means the following. You know, if you do this, it's a totally different thing. That means you have A, B, and pass through a not, and then go into an and. Oh, sorry. This is not an A and D. That makes sense, right? So you have to write it in this way. The bar should cover the whole content you want to invert. Not only like, no, this is not right for an A and D. Okay, so let's try to understand what's this circuit doing by listing out. This is actually Manny started to talk about this, but he hadn't covered it yet, which is the how to say, logic, or the we will have so many equations in the future, and this is what we're going to talk about. So let's give it a try. First one is NA and D. What is X? X equal to NA and D, A and B. NAND A and B, which is kind of one. You can also follow me to write it down. So it's A and B, right? And it's NAND. That makes sense? Great. And secondly, how can we get Y? How do we represent Y? Y is just, did I tell you the symbol for XOR? No, I didn't, right? I use this one.
I don't think we don't have nor.
Nor
And
is,
I don't think we have.
nor is, sorry. This is not. Well, what else? This is and. This is or. Nor and NAND just something with a bar, which is this is and this is NAND. This is or and this is nor, right? So now we have the 6 categories. So the Y is actually XOR of X and C, right? So X and C, we put an XOR here. That makes sense? Finally, we have Z. What is Z? Z is nor Y and not D, right? This is D not, if you agree with me. So Z equals to nor. Let's try to write all first, which is Y plus what? D bar, if I not D, right? There's a not gate here, and we put the bar here. Of course, you can write Z in one equation to plug everything in. I hope that makes sense, right? I know it's a little bit hard to recognize this as beginning. So this is XOR, this is NAND, this is NOR, and this is a NOT, basically an inverter. Okay, so we can fill in the truth table manually now by doing the following. That is A, B, C, D. What if they are all zeros? So what's going to happen here? Any volunteers here?
Could be.
Sorry.
X would be 1.
Yes, 0, 0, and it's 0. So NAND means it's 1. Great. Then after that, I have an XOR. X, does X equal to C? It doesn't, right? 1 is not 0, so it will output 1, if you agree with me, because the input X doesn't equal to C. If you look at the truth table, you see if it's different, the input is different, I will output, oh, yeah, different will output 1, same will output 0. So it's different, so it will output 1. And D is 0. What is here? What's D not? It's 1, right? Boolean login is asking, we will be taught Boolean simplification. Of course, but not in this discussion. I don't want to go too far to cover Manny's job. but I will prepare some questions, and once we have taught that in the lecture, I will cover it. Okay, and let's come back. The final one is a NOR, right? 101 is 0. Oh, sorry, 101 is still 1, right? For all gate, if the input has a 1, the output will be 1, but it's a NOR, so it's 0. Is everyone following? So if it's OR gate, I will output 1, but it's a NOR gate, which means we add an N in the beginning, we are flipping it. So I can fit it 1, 1, 0. Okay, similarly, can any volunteer do the next? I will give you a random example.
I can do it.
Awesome. So let me give you an example first. 1, 1, 0, 1. Okay. So should be 1, 1, 0, 1 here. Okay, let's try it together. Great.
Okay.
So X.
So A and B is 1, but we have a NAND, so it should be 0. So X is 0.
Nice.
And in that case, we have 0, X or 0. They are the same, so it outputs a 1. So Y is 1.
Awesome.
D is inputted as a 1. We invert it to a 0.
Mhm.
So now we have NOR 1, 0. 1 or 0 is 1, but inverted, so it's 0.
Awesome. Thank you. Does anyone else want to have a practice? You know, try to do it before it's homework or, you know, assignments.
I'll do one.
Oh, okay.
Let me erase this thing. I will, you know, erase this to increase the difficulty a little bit. Okay, let me pick this one, probably 0, 1, 1, 1. Okay. Sorry, who said?
I think someone else wanted to go first, but
You
I'll
can
go
take it if
too.
you want. I'm good either.
I can do 3 more examples before I move on to logic sim. Okay, but I have like half an hour, but I didn't take a break, so I want to let you go earlier. So give me 25 minutes. Let's take 5 minutes
Sure.
to more examples. So first one, maybe
Be
DD.
1,
Okay. So what is X?
1.
Let me verify it. 0 and 1. If it's AND, it's going to 0, but it's inverted, so 1. I agree.
Okay, and then the next is 0.
It's X OR. We have the same input, so it's output 0. So
And then it would be 1.
Here,
It would be 1, 0, 1.
1, 0, 1. I agree. Just to make sure, I don't think I will let you do this during exams because, you know, it's purely labors instead, and you can make so many mistakes in the beginning. So I don't expect this kind of questions, but maybe a simple circuit for the truth table. But typically, truth tables, I'm just give you a little bit hint in the future. While you design combinational logical circuits, you will have to design the truth table first, which means I have some inputs. What's my desired output? So I write down the truth table first. Then I try to write equations about simplify the logic, and then finally use the minimum possible gates to implement the circuit. That's how you design a combinational logical circuits. By combinational, I mean there's no memory. So we just have a batch of input and immediately a batch of outputs, which is combination of these gates. That's why they called combinational. But again, that's just some random thoughts I have, not for this week. Okay, next one. I remember we have one more volunteer. How about we do this group? 0, 1, 0, 1.
I can try this one. Okay, so the first one's NAND, so 0, 1 is going to be 1.
Good. Remember, if it's AND, it's going to be 0. So if flip it, it's going to be 1. Great. X.
Right. And then the next one's a XOR, so we have 1 and 0, which is going to give us a XOR, that would give us a 0, right?
XOR. Take a look.
Oh, wait, no, I'm.
Different this.
Oh, sorry. Okay. It would give us a 1 then because they're different.
I'm still making this kind of mistakes. So should
And then last one's a NOR with 0 and 1. So then that would be 0.
Okay, great. So we have 1, 1, 0. Okay, anyone has any questions? Any more questions? I think so. If not, I will probably move on to the logic sim, if you agree with me. You all have this installed, right? If you have problem with installation, you can probably come to my office hour. And I assume you already followed Mani's instruction to download it. It's very simple. Just follow that instruction, click on it, but make sure you have the right version. Otherwise, the auto grader will maybe make some huge errors, and you will lose all points. Unfortunately, Mani is not very forgiving in that case. I have to warn you. So make sure you are getting exactly the same version, which I believe is 3.7.2.
Yeah, as long as it says 3.7.2 at the top of the program, should we be good? Or is there like another way we can verify that we have the?
That's good enough. I mean, when you download it, it's always have that three numbers with you. So, okay, so I'm going to switch to my computer and share the screen again. By the way, my desktop is a huge mess, but so logic sim. This, I would say this software is very intuitive. I use it for the first time actually, because when I learned M16, I use a very different software, but this one is also intuitive. All this kind of EDA tools looks the same. So today I'm not going to cover something related to time or memory, which is sequential logic. I'm no need to say combinational logic, which you can see. Can you see my mouse? Okay, good. So if you see where I'm clicking, it's an input pins. So it's facing, it's left facing. So I'm just going to recreate the circuit, but I would like you to actually create something on your own. While I'm drawing this, I have to emphasize the rules of the academic honesty. Never in this class, never try to, for example, others create some file, you just that's what I heard before. Someone just take others project file and flip it, rotate it, so I cannot visually recognize. But there can be tricks. For example, I can send you some encrypted this kind of documents or something buried, some information buried inside. And when you return it, it can have your maybe UID related information in it. If you got a caught, I do see, I think 2 years ago, 3 years ago, Mani reported such cases. So be very careful. And also for some like check or online platforms, try not to avoid using this. Again, you have to devote efforts to be able to succeed in this course. It's not difficult, but there are some rules of thumb you have to be able to practice. Okay, so the thing I'm clicking right now is called output pins. In our case, we only have a Z, so only one output. That makes sense, right? So gates, the first one is NAND, let's check the gates, NAND gate. By default, this kind of gates have two inputs. You can see these two blue dots here, but you click on it and you can see the specifications. You can change the number of inputs because and this kind of logic means I need all the inputs to be 1 in order to output a 1. So which means you can have 3 and 4 and 8 B, C, D, A and B and C and D in one gate. That's also possible. But currently I'm only talking about 2 inputs. You can increase it. Similarly, or as long as there's a little 1 in your input, I will output a 1. That's for all. But XOR cannot do that. XOR you have to have 2 inputs to be compared. But I will do the wiring. For wiring, you can, if you are in the mouse position, you can directly make the connections by dragging it. Of course, you can go to wiring and, oh wait, you cannot do that. You have to drag it. So click and drag. This is too ugly, so I decide to maybe delete this one. I'm using my keyboard for deletion and to make it look better. Yeah, see, this is more straightforward. What's the next gate? It's the OR, right? So I have X as the output. The next one is the OR gate. Sorry, XOR gate should be here. It takes two inputs. The first one is going to be taken from this pin. Another one is taking the output from the NAND, which is here. You can see you can just drag and connect this, very easy. The final gate, of course, I have a NOR, a not, D not. So connected. And the final gate is the XOR, right? Oh, no, sorry. The last one is a NOR gate. The NOR gate will go to the output. What's the input? So one is the output from the XOR gate. Make sure you connect it well. And the other one is from not D here. And finally, we have the output. Sounds good, right? So far, so good. And now that finally, of course, what you can do a simulation. First, add labels. There are two ways to do it. One is you can just change it here by typing A. You see one A jump here. Let me do it again. You click on it, change the label, make it B. This is one way. Another way will be, I'm using the right version. Can someone verify? Okay, good. Because I installed multiple versions of Logisim before. Oh, I don't have that fast. So I remember someone may have a, oh yeah, this one. Sorry. Yeah. So once you see it's circled around the pin, you can add a C here. It's equivalent to what I have just done. So you click on it. It's in this tool, which is labeler tool. You can create labels like this. So whichever you prefer. There are two ways to do it. So this is Z as output. Okay, then we can do a little bit simulation. So let's switch back to this. So you can see the first we have a hand shape, which is to toggle. Oh wait, where's my B? I must have forgot to save it. Okay, you see when I click on it, you can see the state change. This one means high, means one. The green one is high voltage. Let's see if I turn, oh, sorry. You see, 0, 0 makes 1. That's a simulation. C is now 0, D is 0, and output is 0. So I will try to, let's verify one of our previous examples. So when the input is 0, 1, 1, 1, the output is 1. Let's give it a try. 0, 1, 1, 1, the output is 1. So right? That's a simulation. But of course, it's still so tiresome to do a simulation one by one. So what you can do is here, simulate. Then, wait. Oh, sorry. Project, analyze circuit. I'm going to stop here a little bit. Project, analyze circuit. I would suggest you actually, if you have computers around, you can follow me. Analyze circuit. And this is the equation, expression Z equals to the following. And you are going to use this in the future. That's how we normalize, simplify the Boolean logics, but not now. And the table is a truth table, which we were trying to create on the way. You see, that's how you can verify locally if your circuit makes sense before you submit it. But of course, please make sure the labels, the name should all remain to be right. Otherwise, the auto grader might give you some mistakes. And that's
where do you find that window?
Project, analyze circuit.
Ah, thank you.
Mm-hmm. And you can use tables to look at truth table or expression for the minimum. So the last one. Oh, by the way, when you have this, what you can do is to file, export image. Of course, you can save the project file. I don't want to waste time on that. Everyone knows we can save after we make changes, right? But you can also export an image. This what I want to do today. Maybe a JPEG file would do, and just output it. I will put in a, okay, I put on the desktop. Sorry, it's in Chinese. It's my personal computer. I'm at home. So let's see if, see, that's a circuit I just created. This is the output. So I'm going to send a link in the chat to verify you attended the lecture today, which is, where's my Zoom? If it's okay, I stopped the screen sharing, right? I think I covered all the information I need to say. So in the chat. In this one, please type in your information and also create your own circuit using, how to say, using this. Please do not share it to any like GroupMe or Discord. I don't really want to, people who just don't attend any of these sessions to benefit from our link. So make sure keep it just to yourself. And this form, you record your attendance, and please add a picture of your, you can create some random circuits in your logic sim and generate a picture so I can understand you can, how to say, be successful at least next week. That's very important to be able to use logic sim. That's why I need to verify your output. But for feedback, I will try to create, after I collect these forms, I will try to, if you all agree with me, I can create a, how to say, a shared spreadsheet with your UID and your attendance to see if you are here or not. We haven't, remember I had 3%, I haven't set a threshold, maybe I think 8 times or 7 times. I think 8 should be good, but I need to talk to Money this Friday to, give you a right number. But it's a little bit, how to say, violation of privacy because, your UID and your attendance will be there, but I guess it's fine. I will remove your names and email address to protect your privacy if you agree. But if you have concerns or objections, please feel free to reach out to me after class. Maybe I can think of a better way to do it. Maybe a database or something, but that's going to, slightly complicate my life. Okay, so this is 38. I should have 10 minutes. I'll be stay here to answer any questions for today, but otherwise, once you finish the questionnaire, you are free to go, and I will see you next week. For attendance, we have 4 different discussion sessions, so actually you can attend any of them. One is on Zoom, but when we move in person, we might have classroom constraints, but we will suggest attend the same person, which is 1A, 1C or 1B, 1D. You just need to attend 1 per week, but make sure it's the same person because different me and Noyan may have different styles or notations, so you want to keep it straight. And also where we are last time. Like I was successful to cover all the information today, but maybe I will leave a question for future, and that's only known by me. Okay. Okay, any other questions? I will stay here until 50, but if not,